Paul and I are here, part of it, but then we have our collaborators also, both Rudi Podgornik, Adrian Versegian, and William Ching here for the rest of this week who are working on it. We thought that would be a nice time to put together sort of a biomolecular materials set of seminars. And so in this case, Rudi is going to be presenting 3 lectures today, tomorrow, and Thursday at 10 o'clock. We'll also have 2 other lectures today and tomorrow at 11 o'clock in this kind of a broad area. And so therefore, I'll introduce Rudi Podgornik. I have been working with him since about 2000, I think, when I first sort of got connected to Adrian. And for me, as a material scientist, started as a ceramist, this wandering over into biophysics has been a great lateral translation. I've just learned so many different things. So thanks a lot.
Thanks, Brian. So I'm happy to see some old friends in the audience. I was here a few years ago at the physics department, right?
Absolutely, yeah.
Absolutely. And I'm not sure what I talked about at that time, but hopefully something different. So this is the first talk at this meeting. I'm supposed to give 3 talks, a series of talks on molecular attractions, as I call them. So I will, yes?
Can you go a little bit of black and white?
A little bit?
Yeah, I can figure out our...
Like this?
Yeah.
Yeah? No, this is good.
So you have to just try all these buttons. That one. No, that's worse.
Yeah,
That one's not bad.
No, but it turns
Yeah,
out
but it's shining light on the screen.
Yeah.
Yeah.
Turn the one off on the screen, that's all. Turn the rest on.
No, no, you got that's about...
It's good.
Yeah, that's good.
Can you not have the back lit?
No. These are like complicated systems, right? Complexity. It's time to do all kinds of simple questions.
So I will talk about attractive interactions mostly in a theoretical context. I will not address any experiments in my talk, or just maybe mention it, but I will not go into details. So this will be about the theory of molecular forces. Specifically, I will discuss the van der Waals interactions, which are a ubiquitous source of attractive interactions, sometimes also repulsive interactions. Specifically in soft matter, I'm going to close this door, but also in hardcore condensed matter, liquid crystals, and so on. The next topic will be electrostatic correlation interactions. This is connected with the usual theory of electrostatic interactions, referred to as the Poisson-Boltzmann or mean field theory. And I will tell you what happens when the mean field theory is not applicable anymore, where for some reason we cannot use the Poisson-Boltzmann equation. What do we do then? And what can we expect to see? And the third source of attractions in soft matter is the polyelectrolyte bridging interactions, which are another interesting type of interactions. In fact, polyelectrolyte bridging interaction is a classical equivalent of atomic bonding in molecules, because very similar equations are used to describe both. So polyelectrolyte mediated interaction is a little bit like a chemical bond, but of course the strength is different because all the constants in the equation are different, but the equation looks like the Schrödinger equation. So this is the plan for the lectures. I will not go into much detail on any topic, but I will try to give you an overview of molecular attractions, of the world of molecular attractions. If you have any questions, please do address them while I'm speaking, or you can get it to the end and then ask your questions. So, plan of the lectures, as I said, van der Waals interactions, which are due to correlated electromagnetic field fluctuations in space, meaning between the dielectric bodies or within the dielectric bodies, electrostatic correlation interactions, which are due to fluctuations of the local density of charge carriers like counter ions or salt ions, and so on, and polyelectrolyte bridging interactions, which are a little bit different in nature because they involve polymer materials and the connectivity of the polymer materials, and will be described on a little bit different level. So let us start. Van der Waals interactions, correlated electromagnetic field fluctuations, and these are the characters I will be mentioning in our talk quite a few times. Van der Waals, Casimir, and Lifshitz, as you can see them, probably recognize them. And I assembled a set of quotes regarding each of them. As for Van der Waals and his equation of state, Leibowitz in 1985 says his equation of state was so successful that it stopped the development of liquid state theory for 100 years. So it's better not to have two theories that are too good, because then nobody has any incentive to come up with something that's better. So that's his opinion about Van der Waals. Casimir, he was discussing his calculation with Bohr, and he said, I mentioned my results to Niels Bohr during the walk. That is nice, he said. That is something new. And he mumbled something about zero-point energy. And zero-point energy of quantum electromagnetic field fluctuations is still the basis of our understanding of Van der Waals attraction, but need not be so. There are other ways to formulate the theory which don't address the zero-point energy at all. And then Lifshitz, of whom Ginzburg said his calculations were so cumbersome that they were not even reproduced in the relevant Landau and Lifshitz volume, where, as a rule, all important calculations are given. Lifshitz tour de force of 1955, 1954 was a very complicated theory, putting or assembling together quantum mechanics, statistical mechanics, and electromagnetic field theory. So some people say, and Lifshitz himself thought, that this is the best he did in science, and this is coming from a guy who really did a lot of pretty cool stuff, but he thought that his theory of Van der Waals interactions is the best that he did, because it brings together so many, three very different aspects of physics into a single theory of molecular interaction. So these are the three characters. And we can say that it all started with Lebedev and his PhD thesis. This was in the time, or around the time, when Maxwell formulated his theory of electromagnetic field, and then Hertz showed that, in fact, the electromagnetic waves are connected to this theory of electromagnetic field. And Lebedev was thinking about how the electromagnetic field is connected with interactions between molecules. And he says that there exist between the molecules, in such a case, molecular forces whose cause is inseparably linked with the radiation process. Right? This was his vision. He didn't really calculate anything, so he just put this thought into his PhD thesis in 1894. And apparently Lifshitz read this thesis and got the idea for his calculation, which was based on Lebedev's sort of vision and Casimir's calculations, as we will see. So Casimir in 1948 started working on this problem by looking at the electromagnetic field equations, which are written right here in empty space. Electromagnetic field equations have a solution in terms of waves, harmonic waves. And if you are in empty space, of course, you have a distribution over all possible frequencies and the corresponding wavelengths. But if we consider a delimited part of space, where you have two ideally polarizable surfaces, like metallic surfaces, that do not allow the penetration of the electromagnetic field, which is an idealization, as was realized by Lifshitz. So at high enough frequency, any material would become like a vacuum. So saying that the field cannot penetrate a surface at any frequency, of course, is idealization. But this is what Casimir assumed in his calculation. And obviously, in the space between the metallic surfaces, only those waves can fit whose wavelength is related to the separation between surfaces. Like a multiple of the wavelength should be equal to the separation. And these are the eigenfrequencies. You can do, you can solve, of course, the two wave equations for the E and H fields. And these are the eigenfrequencies that you get. You see that they depend on D, which is the separation between the surfaces, as well as L, which is the size of the lateral size of the surface. By introducing this wave vector in the perpendicular direction, so within the plane of the surfaces, I can write the eigenfrequency in this case, in this way, assuming that L is very large. So I go to a continuum representation of the solution. Now, the way Casimir was thinking is that if you have these modes in space and in the space between the surfaces, with each mode you can associate at zero temperature 1/2 h bar omega energy. This follows from elementary quantum mechanics. You know that in quantum mechanics, because of the Heisenberg principle, you can never have the system cannot, the lowest energy state of the system does not mean that the system is not in motion. If you have a harmonic pendulum, classically, of course, the lowest energy state is the pendulum is just in its minimum free energy state, and it's not moving. That's the lowest energy state. In quantum mechanics, because of the Heisenberg principle, it has to move also in the lowest energy state. And this motion corresponding to the lowest energy state, it has an energy of 1/2 h bar omega. And if you sum this energy for each of the electromagnetic field modes between the surfaces, you end up with this famous Casimir result, giving you an interaction energy that decays as d to the 3rd power. And it goes obviously as the square of the surface area of the two interacting surfaces. This is apparently a quantum effect because it contains h bar and c, as you can see. And it's a long-range interaction, 1/e to the 3rd. So a way to see this interaction, the Casimir interaction, is to look at the modes like some kind of maybe polymers of a certain size. And you know that if polymers are excluded from a space between the surfaces, you get a depletion interaction because polymer outside are pushing on the surfaces from the outside, pushing them together, and this is like an effective attraction. So Casimir interaction, one could say, in principle, it's like the electromagnetic depletion force. Loosely, I'm not trying to say there's an exact correspondence. But loosely, conceptually, that's what it is. So the size of the interaction is right here. If you have 1 square centimeter area, 1 micrometer apart, they interact with the force of 10 to the minus 7 newtons. And the smaller the separation, the bigger the force. That's why Feynman, in his lecture on, there's plenty of space at the bottom, about the nanotechnology, so to say, realized that these are the interactions that are going to be most important in the nanoparticle. And that's why we still study them. And it turns out that they are quite complicated interactions, as you will see as I proceed. So, you know, in physics, it's nice to find forerunners of an idea. Where did we get this idea from? And one possible forerunner is a book published in France by Causet. It's called L'Alban du Marin. So this is a sort of handbook for sailors. And it published in 1836. And he says that if you have, this is taken from that book, if you have two ships on a rough water surface in an ocean, because of the waves hitting the ships, they push the ships together. Yeah? And he says that there is a certain force of attraction, une force certaine d'attraction, a certain force of attraction between ships in the rough sea because of the waves on the sea. This is very similar to the Casimir vision of the electromagnetic field fluctuation interaction, except that here the fluctuations are in the height of the sea. This is waves, but the idea is similar. So many people have noticed this effect. I took this from, I think his name is George Nolan, and he describes a regatta in Australia in 1998. I'm not going to read it, but you see that what he observed is that in a rough sea, all the boats were sort of cramped together because of this Casimir-like effect. Mind you, this is not the same as the Bernoulli effect, which the sailors know. So if a ship goes past another ship at a small separation because of the Bernoulli and the motion of the liquid in between, they are pushed together. This is a different effect. Yeah, this is purely fluctuation. So this is again from the book, a little bit more. On a calm sea, there's no interaction, but on a rough sea, apparently, according to this guy, there's some interaction. But then when you look at his depiction of this situation, you realize there's something wrong, because the waves are just too big. In order to get this kind of Casimir-like repulsion, you need the amplitude of the waves and the wavelength to be comparable with the separation between the boats. And that's not the case in this situation. So there's a huge discussion in the literature. I took this from the Nature site a few years ago. So this was in 2006. Some people said, well, no, this doesn't really look like the first intuitive understanding of van der Waals interaction. It's different because the waves are too big and so on. But I think it is a kind of an intellectual precursor of the Casimir interaction. And later people actually calculated this force on a rough sea. Sitko Boersma calculated that and published his results. And the interaction indeed is a long-range interaction falling off through the power of the separation between the boats. Back to our story. After Casimir calculated his interaction, Lifshitz noted, of course, that the calculation is based on very severe assumptions. And the biggest assumption, according to him, was that the surfaces always respond as ideally polarizable matter, meaning ideal conductors, with no penetration of the field. That's obviously a very, very far-reaching approximation. And if you want to talk about interaction between realistic surfaces, interactions in a realistic manner, you have to improve this, because this is not really capturing the actual properties of matter. And the way to improve that is to assume that you have a certain frequency response of the dielectric function, epsilon of omega, which depends on the type of the material. And this is another separate part of the electromagnetic field theory, the properties of electromagnetic fields in matter. And we describe those with the dielectric permeability and magnetic permeability. For many materials, magnetic permeability is very close to 1 at all frequencies, so we don't bother with that. But epsilon is not always close to 1. In fact, it varies a lot. As you know, static permittivity of water is about 80, ice around 94, and so on, and it varies with frequency. And Roger can tell you much more about that because he measures this kind of response of the materials. So if you have a material and you measure the effective field in the material, it will depend on what is the frequency of the driving field. For every frequency, there's going to be a different frequency response. So Lifshitz assumed that we have two bodies interacting across vacuum. Why across vacuum? It's a nice technical point, because he used the electromagnetic stress tensor, Maxwell's stress tensor, to calculate the forces on the bounding surface. And the electromagnetic stress tensor for a general material that has a frequency-dependent dielectric permeability is not defined. Because the energy is also not defined, because you can have losses. And if you have losses, there's no real Hamiltonian, because it's not conserved. So that was the problem. That's why he thought, okay, I can't do it in general, I will do it in vacuum, because in vacuum, for sure, this is true. Maxwell's stress tensor in vacuum, of course, is always defined. So let's take a vacuum layer with epsilon 1, no frequency dependence in the dielectric response function, and two bounding materials, epsilon 1 and epsilon 2, or maybe the same epsilon 1 equals epsilon 2, which have a dielectric response function, so epsilon omega. That means that as opposed to the idealized Casimir calculation, where there is no penetration of the field beyond the ideally polarizable surface, in this case there is some penetration of the field depending on epsilon of omega of the material of which the surface is composed. That's the main difference. So he wanted to calculate the modes for this situation, he wanted to solve the electromagnetic field, the wave equations for this situation, insert the solution in the stress tensor, and then average the stress tensor. That was his plan. And this is in fact what he did in 1954. He saw the calculation through. It's a very heavy calculation, very difficult to follow. Today sometimes I give it to students just to read, but not to reproduce it, because it contains many tiny details from thermodynamics, statistical mechanics, electromagnetic field theory, quantum mechanics, which are maybe too much to absorb at the first reading. But it's a very interesting paper, one of the classic ones in physics.
Why does that frequency-dependent dielectric function of the materials not appear in the stress tensor still?
Oh, it does. It does. Okay, it does too here. So you see in the matter, the Maxwell equations are of this type. And you need the so-called constitutive equations to connect the D field, dielectric displacement, with the electric field. These are usually linear, and for an isotropic medium they're scalar, but in general they're nonlinear, and there's a tensorial dependence of epsilon. Okay? So in the matter, of course, apart from the Maxwell's equations, you also need the constitutive relations which connect D and E and B and H. That's the way you formulate the electromagnetic field that we are doing now. So this is what you need to assume, and then you take into account the boundary conditions at the surfaces, you solve the Maxwell's equations, you take into account the fluctuation dissipation theorem, which connects the correlator of the electromagnetic, the vector magnetic potential with the response function and the temperature and frequency. You put everything together and you can calculate this average. It's a very heavy calculation, as I said a few times now, not trivial, and that's why Ginsburg says it was so complicated that they couldn't even put it into the textbook on theoretical physics, because they needed to work out the details before this is done for people to be able to follow. The result is written as follows. This is the expression for the pressure between the surfaces. You see that it contains an integral over P, and then it contains a summation over N, and this omega N are discrete frequency referred to as the Matsubara frequencies for the room temperatures. It's about 10 to the 15 hertz. Times n, which is the order of the Matsubara frequency, and you sum over all n's. But what's more important is that the whole expression here depends on, not on epsilon of omega, but on epsilon of I omega. You would think, what's the frequency, what's the dielectric response function dependence on the imaginary frequency? That's just ridiculous. But it turns out, by the Kramers-Kronig relations, this is a perfectly well-defined function. As you can see here, that's the definition. It monotonically decays with the frequency, and it's a real function. So epsilon of I omega is a perfectly well-behaved function. And if you think a little bit more, epsilon of omega corresponds to the response of the system to an external field with the frequency of omega. Epsilon of I omega corresponds to a fluctuation, spontaneous fluctuation of the electromagnetic field that decays with the characteristic time 1 over omega. I omega, if you look at the time dependence, you get I times I omega t. This is minus omega t. This is like a decay. And this is the decay of spontaneous fluctuation. So what the Lifshitz formula is telling us is that this interaction depends on spontaneous fluctuations of the electromagnetic field in the bodies and in the space between the bodies. That's the physical picture behind the calculation. And when you know that, of course, you can formulate the Lifshitz interaction, Lifshitz-van der Waals interaction in different ways, not considering the electromagnetic field fluctuations, but fluctuations in the charge density or the current in the interacting bodies. But that's the same. It's exactly the same thing. So van der Waals interactions or Lifshitz-van der Waals interactions can be formulated from different perspectives. They all lead to the same result. So this is a typical dependence of epsilon on I omega, and this is specifically for water. You start with 80 and then you go down to 1. That's the dependence.
In this formula, we are summing over all the frequencies.
Yeah?
How do you choose the range of frequencies?
The range of frequencies, it's from 0 to infinity. So it turns out that the 0 frequency is very special, n equals 0 is very special, and that corresponds to classical fluctuations. Whereas all the higher order terms, n equals 1 and higher, correspond to quantum mechanical fluctuations. And there are other ways to calculate the 0 frequency term through ordinary classical statistical mechanics. So either this way or the other way.
You might just tuck in there that epsilon at 0 frequency actually never happens as a pure 80. That in fact, you're usually measuring it at 10 to the third or so hertz because all materials have some conductance. And there's a paradox.
Conduction, of course, is
which is quite important sometimes when you're dealing with salt solution.
Yeah. So I'm not talking about any conductive media. This is purely dielectrics.
Ideal dielectrics.
Ideal. Yeah. Just for the sake of introduction. So anyhow, this complicated expression has various limiting forms. For small separations, it goes to 1 over d to the 3, to the 3rd power. And A is the so-called Hamaker coefficient. And the Hamaker coefficient, if we compare this formula with this formula, you see that it's a complicated integral over frequencies, zeta, of the expression in the square brackets. And for large separations, it turns out to go to the Casimir result. So the Casimir interaction would be just a limit of Lifshitz interaction. There's a little bit of a mismatch in the field. Some people are very strong about Casimir interactions. They feel strong about them, and they think that they're not related to van der Waals interaction. This is something completely different. That's not true, in my opinion. And indeed, the Casimir result is just a limiting form of the Lifshitz result. So 1 over d to the 3rd. 1 over d to the 4th, of course, because we know from the Casimir calculation that energy goes as 1 over d to the 3rd. So you derive the energy, you get 1 over d to the 4th, as opposed to 1 over d to the 3rd for small separations. We call this the non-retarded result, and we call this the retarded result, because it turns out that the different power dependence on d is a consequence of the fact that the velocity of light is finite. So it takes some time for disturbance to propagate from one side of the slab to another one. And that's why we get a higher power dependence in the interaction energy. So non-retarded versus retarded.
What is the short and the long here? The short separation and the long separation?
Excuse me?
What is the short separation limit?
Well, it depends on the details of the dielectric response. Yeah. But there are these two limits. So remember, this is all for two interacting media across vacuum. Lifshitz could not resolve the issue of how to calculate the stress tensor in a dielectric material, in an active medium that has a dielectric response itself. So this was the next step, accomplished in 1961. So it took a while to figure it out, how to actually do the calculation. And this is another classical paper in physics, in theoretical physics, the general theory of van der Waals forces, where these three guys, so Zieloszynski, Lifshitz, Witajewski, of the three guys, Lifshitz died, Zieloszynski retired a few years ago, right? And Witajewski is still active in the field, producing papers on van der Waals interactions. And he works somewhere in Italy, University of Trento. Unrelentingly. Of course, on some modifications of the van der Waals interaction, because most of the basic stuff for ordinary van der Waals he has figured out years ago. So this is the geometry. You have two media interacting, dielectric media, interacting across the third medium with its own frequency response. And the interesting thing, I'm not going to go into details, but the interesting thing is that for this case, the interactions are not purely attractive, as in the case of vacuum, between two identical media, but they can be attractive as well as repulsive. This is known since 1961, and there's a nice experiment by Sadisky and Anderson on the liquid helium climbing up a wall, which is due to the repulsive interaction across the helium layer between the wall and vacuum. 1961, experiment 1970. So a few years ago, it's made a big splash. Some people calculated the same kind of interactions, called it quantum levitation. And they thought that they have something, but in fact, this is known from a long time ago, that van der Waals interactions can be repulsive or attractive. So we have these are the two cases. If dielectric profile goes like that, you have a repulsion, and it goes like that, it's attraction. Very simple. And actually there have been observations of this effect for various materials much later. So the last paper I know of was Adrian's paper a while ago, 2 years ago, right? Yeah. So this is ongoing. Why is this an important issue? Because you want to tweak the van der Waals interaction from attraction to repulsion between various media, and you could use the tweaking for some technological applications. So that's why it's a hot topic.
And you know it's coming to the mainstream when Dartmouth has a program to exploit the Casimir effect.
Right, right. Many people are trying to do that. Many people are trying to do that. So there's a guy in California who's got, actually it's a business, right? I think it's called Galactic something. Yeah. Galactic technology. Intergalactic technology. Yeah. And he's trying to come up with a gadget that will use this kind of effects. So anyhow, after you have the result, you can start thinking of how you're going to derive it in a simpler way, so that you can, of course, teach the students how to do it. And for a while, it appeared that the Lifshitz calculation is so complicated that fine, you know, they calculated it, but what are we going to do with it? We can't generalize it, we can't look at other cases. There's nothing to do with that theory because it's too complicated. So Van Kampen and then Adrian came up with a different derivation. Van Kampen for zero temperature, and Adrian and his colleagues at the non-zero temperature. We're just looking at the electromagnetic field modes and the 0 point energy for t equals 0, and the free energy at finite temperature of these modes for finite temperature.
Could I just interject a very nice story? You know, important sociology isn't science. I was in Holland, and my advisor told me Van Kampen is rederiving Lifshitz in a simple way. I went to see him, and he was so nice to me. he sat down with me and we went through his notes before he published this paper. This was 1967. And he so generously showed me every step how he's doing it. This kid just walks in his office and he just showed the whole thing like that. And that liberated me to think I could work on this subject. So it was getting away from the dry stuff. The personal stuff was magnificent.
Mm-hmm.
And I think that the kids here should know that they can be in a good world sometimes.
So this is 1972. This is referred to as, or was referred to as a heuristic derivation, because some people thought it's not mathematically exact, until Barash and Ginsburg in 1975 showed, in fact, that it is completely okay. There are no loose ends in the derivation, and it's just an alternative way to get to the Lifshitz result.
Rudi, could I interrupt just again? This use of the word heuristic is a really nice point that Barash and Von Kamen were talking differently. We always think of oscillators, and that can happen in a vacuum because they're just oscillating, nothing's impeding it. And the big issue is if you have a dissipative medium, are you still allowed to use oscillators as pure sine wave oscillations?
That's a
So it's non-trivial to convince yourself that you can look at the sinusoidal part when you have the things actually dying from dissipation. It's a very nice thing to think about. It sounds a little arcane, but it's in fact, it goes into a lot of the physics of what's going on.
So this is part of the result. I'm just going to skip this. This is the general result for finite temperature above the complicated formula. And this is a very active field, as you can see. Lots of books on the Casimir/Van der Waals interactions. I'm still not sure why some people get so excited about Van der Waals being different from Casimir. But I guess the reason is that the Casimir interaction can then be generalized to different field theories, quantum field theories, where it has a little bit different context. And they always refer to them as the Casimir interaction in that context. Whereas Van der Waals interaction is more about interaction between real materials and not just some abstract effect of a different field theory, different symmetries in field theory and so on, but it's about materials and interactions between these materials. So these are the three latest books that, well, not latest anymore, but this is, as I said, this is a well-developed old field with ancient animosities, in case you want to work in that field. Now let's go to some numbers. So let's go to a small separation limit, the non-retarded limit. And this, as I said, this is referred to as a Hamaker coefficient.
Who is Hamaker?
Hamaker. Hey, who is Hamaker?
Hamaker worked at the Phillips factory where they were doing early colloid theory. And the theory of Van der Waals forces at that time was really coming from the Van der Waals gas, which we know has this attractive term correcting the pressure, the A over the Q term. The question was, if you're making colloids, condensed materials, can you carry over the idea of the gas to the colloid? And the point is that you have inverse 6 interaction between point particles, which we all learned. And some of us learned incorrectly, came from the Van der Waals gas equation. It comes from some other reasoning. But the huge question was, can I make believe those big blobs of solid material are attracting each other as though the points inside of them are still atoms? The so-called pairwise summation over the parts. And Hamaker did the summation for different shapes of materials, to spheres, to planes, where there were condensed media, not gases anymore. And the Hamaker approximation is, I'm going to make believe that the small parts of those materials still attract as there were inverse 6 particle interactions in gas. So that's the so-called Hamaker approximation. And he got a coefficient that came out in the case of 2 planes that it was coming as inverse square for the energy. For spheres, it would go from inverse first power at close distances and then properly go over to inverse 6 when they're very, very far apart. It became religion at that stage, and it was used in colloid science from that time until Lifshitz came along, that you could make that pairwise summation. the coefficient was completely adjustable. If you look at the papers of that time, you found there were fitting colloidal aggregations with coefficients that vary over a factor of 1,000. There was just no intuition about it, what it should be. It was only when it came back to Lifshitz, and then they could take the spectrum, Rudi's going to talk about it, what those coefficients really would be. But the idea of the gas is coming back. Yeah.
So let me continue.
I'm sorry, Rudi, it's too long.
You have various estimates and calculations for the chemical coefficient in different materials. And I have to tell you right here that there's a big difference between the Casimir and the van der Waals community in the units that you use for van der Waals coefficients. And this is in the solid state physics, you use zeptojoules, 10 to the minus 1 joules, to express the van der Waals coefficients. And in soft matter, you use KT units. They're, of course, the same. Yeah? But people cannot talk with one another because of the unit problem. You say, well, it's 10 KT. You say, what? 10 KT? It's not 10. It's 20 zeptojoules. Completely different, and so on. So anyhow, from the spectrum, this is epsilon of omega for water. This is epsilon of imaginary part of epsilon of omega. So this is the real part and the imaginary part. And you see the frequency dependent. You have these huge peaks. This one is due to the biorelaxation, infrared relaxations, optical windows, ultraviolet relaxation, which is what Roger measures for various materials. And based on the spectra and the Lifshitz formula, you figure out what the Hammocke coefficients are. Hammocke coefficients are always for interaction between different media across a third medium. You can't just say Hammocke coefficient. You have to specify what is the nature of interacting bodies. There is also a possibility now to measure dielectric response, not to model it in some way, but measure it directly. So this is from Roger, 2003, strontium titanate. They can measure dielectric response across a grain boundary of a crystal, and you get the dielectric response from that experiment directly. You don't have to model anything. So you just insert this. So this is the original dielectric response. Then you go to the epsilon of I omega, and you can calculate the corresponding Hammocke coefficient right here in zeptojoules, because we're doing crystals. So it's not KBT, it's zeptojoules. There's a nice program, of course, for that, developed by Roger and Lin, called Hammocke, called Gecko Hammocke, and it contains various spectra, and you can calculate interactions between very complicated geometries, and it's available for your download. It's freeware, and anybody can use it and calculate van der Waals interactions. So experimentally, this has all been tested. This is an old paper, maybe the first quantitative test. Shi and Precision in 1975. They were shooting atoms over a surface, and due to the deflection, which you interpret as the action of van der Waals interaction, you get the separation dependence of the interaction, and you can compare that with the Lifshitz potential. So here is the comparison. These are experiments. This is the Lifshitz prediction. It works pretty good. There are other experiments, more recent ones. Some experiments have problems because what's the problem in an experiment like that? There are so-called parasitic effects, so much larger interactions that hide the underlying small van der Waals contribution. And you need to subtract the large contributions properly to get the van der Waals contribution. And that's an untrivial thing to do. So this is Mohideen and Roy, 1998. Predictions and the actual experiment looks pretty good. I will not go into details. It caught the attention of the media, of course. The power of nothing. Who would like that? Quantum foam, and so on. And there are different variants of the van der Waals interaction or the Casimir effect. That's a pretty cool one, I think. So this is the acoustic Casimir effect. Instead of having electromagnetic field, let's have acoustic. Acoustic field is just sound. So you see the two big loudspeakers here, and there are two plates, and you turn on the loudspeakers and drive them with noise. It can be white noise or some other noise. And you look at the plates and you will see that if you tune the speakers properly, all of a sudden, the two surfaces jump together because of Van der Waals like acoustic interaction. Very cool, very cool. So this is 98, La Razza and Denata. They measure and calculate. So that's the calculations. And so the calculations are a little bit different here because these are not spontaneous fluctuations, spontaneous acoustic fluctuations. They are driven acoustic fluctuations. But in general, simple. So the famous case of Casimir effect in vivo. This is gecko. If you've ever seen gecko, you can take it and throw it onto the ceiling, and it sticks to the ceiling. You can walk on the ceiling. Very interesting animal. And it sticks because of Van der Waals interactions. And it's got special type of feet that allows him to use the Van der Waals interaction for sticking. And people have measured that, calculated that, and so on. I will not go into detail, but you see the nice detail. In the foot of a gecko, there's this spatula, which is sort of flat at the end, and he can put it close to the surface, close enough to feel the Van der Waals interaction. And a special trick, of course, it must use to peel it off, because it's not important only to stick, but if you want to walk, peel it off. And this animal has figured out all the details and intricacies of Van der Waals interactions and how to use them. We understand them probably better than the gecko, but we cannot use them to the same extent as this animal.
Gecko understands it pretty well.
Pardon?
So the gecko seems to understand it well enough.
Yeah, on an intuitive level for sure. But I think he's not aware of the Lifshitz point.
Can you still use it in the surface as well?
I think so. Yeah, they've tried all sorts of tricks with gecko, and it always seems to be able to
Rust
stick to the
can be a
surface.
help because it gives you more contact area. Dust can be a problem.
Dust can be a problem, of course. And they eliminated all other possible sources of attraction. There was the suction, which I find fascinating. You know, they eliminated the hypothesis that it can stick to the wall with suction. How do you do that? You have to do the experiment in ultra vacuum. How you do that with the gecko, I don't know.
I have to confess, when I first heard this, I actually thought they were mad to think that the Van der Waals interactions could be so useful.
It turns out it is. All the calculations confirm. So now to some modern developments, modern meaning the past 10 years, let's say. The effect of boundary conditions. You asked me about rough surfaces. There you have it. This is a rough surface. Two rough surfaces interacting lead to a little bit different dependence of the interaction-free energy. There's a term for ideally smooth surfaces, and then there are other contributions. They are subdominant, so the power, h is the separation. The power of 1 over h to the power is bigger than 2. That's what I mean by subdominant. So the dominant effect is still standard Van der Waals constant. But you need to figure out what the effect of vacuum fluctuations would be for these two kind of very rough surfaces coming together. Then there's the effects of the geometry. I have always talked about interactions between planar bodies. Of course, not every body is a planar body. Most of the bodies, especially in biophysics, where we have spherical cows, they are spherical, as we well know. So you have to figure out what the interaction of spheres or cylinders is. And more specifically, what is the self-interaction of a sphere? And people started talking about that, and you can figure out what the dependence should be. So it should be 1 over radius for the Casimir interaction. This is self-interaction of a sphere, of a metallic sphere. So you have fluctuations of the field inside, there's a metal sphere around them, and because of the fluctuations, there is a pressure on the spherical boundary. And people thought that, of course, this interaction has to be attractive, sorry. I spoiled the story now. So it has to be attractive because Casimir interactions are attractive, and it has to fall off as 1 over the radius of the sphere. And after extensive calculations, it turned out it's not attractive, it's repulsive. Very strangely. So you would think that it's like in the Podgornik experiment where you have vacuum inside the sphere, and you see the horses cannot pull the spheres apart, the two parts of the sphere apart. The vacuum fluctuations of electromagnetic field in a sphere will be pretty much the same as the effect of the external air molecules on the sphere with vacuum inside. But it turns out, as I said, that interaction, self-energy corresponds to repulsive interactions. Why is that? Because not every mode outside pushing the sphere together acts in a mechanical way, pushing together. Some of the modes just scatter on the sphere. That's the difference. So you have to take into account the scattering contribution and the general Maxwell pressure of the modes on the boundary of the sphere. That's why you can't say offhand whether the interaction is going to be repulsive or attractive. And in this case, it turns out to be repulsive. So it completely ruined Casimir's own argument for the finite size of the electron. There's the so-called Casimir model of the electron, which basically says that an electron is a infinitely polarizable spherical surface with charges on it that self-interacts with the Casimir interaction. So you could see this in this model. The electron we described, the energy, is the electrostatic self-repulsion of the charge smeared on the surface, and van der Waals or Casimir attraction with a minus, assuming that it's attractive. And you can obviously calculate the equilibrium size of the electron from this. But because there's a sign difference here, we can't really do it. So Casimir model.
Z?
Z is just a constant. You don't know what the numerical coefficient is. So drastic effects of the geometry.
So the first one was just the self-energy.
Yeah, electrostatic
Yeah, the old thing. Yeah.
People talk about pseudo-Casimir interaction. You use the word pseudo when the fluctuations are not due to electromagnetic field fluctuations, but to some other order parameter fluctuations, like density fluctuations, close to a critical, or vector fluctuations in a nematic liquid crystal, or a spherical liquid crystal. In all those cases, you have the same kind of fluctuations that lead to a similar kind of long-range attractive interactions. And we refer to them as the pseudo-Casimir interactions. So this is just the case of critical fluids. Fisher and Dejean, 1978, a very hot topic of research right now because people have figured out how to approach the critical point with a certain liquid between two solid bodies. And as you go through the critical point, it all of a sudden sucks the two bodies together because of the pseudo-Casimir interaction. There are experiments, and people claim in these experiments that this is actually what you can see in an experiment. This is the work of Dielectric and his group, a very nice generalization of the concept of Casimir interactions. That's actually measurable. So there are all sorts of other cases where you're going to not measure anything, but in this case, they measure something. So this is the pseudo-Casimir effect in liquid crystals. I think Phil knows more about that. And the fluctuating quantity here is the nematic director, as you can see right here. And if you look at the thermal fluctuations of this director around some mean field configuration, you get to similar interactions as in the electromagnetic case, but the dependence on the separation is different, of course, more complicated because the free energy that you need to start with is different than in the electromagnetic field case. But it is still the general principles of the interaction are exactly the same. There's also a pseudo-Casimir effect for salt solutions. If you have ions between charged bodies, they fluctuate around the mean field. The mean field is described by the Poisson-Boltzmann theory, the Poisson-Boltzmann equation, and you can calculate the pseudo-Casimir interaction due to those interactions. There is a case, which is my favorite, because it's unresolved. If you look at the classical paper from 1961 Zeloshinsky, Lipschitz, Gudayevsky, you will see that in, I think it's the last paragraph, they say, and obviously, for hydrodynamic fluctuations, we have a similar interaction that falls off as such and such power, and the prefactor has this form. And many people have tried to reproduce this result. And there are two completely divergent schools. The first school says, yes, this is the case, we can do the calculations, this is what we get. And the other school says, no, it has to be zero. There's some very general arguments for the interaction in case of hydrodynamic interaction to be zero. Why? The basis is that in a classical, this is all classical, so this is not quantum mechanics, it's all classical. In classical statistical mechanics, you know that you have an interaction over the positions of the particles and the momentum of the particle. And the momentum integration is separable, right? You can integrate out the P, and you remain with the configurational partition function. But the fact that you can integrate out all the velocities, or the moments of the velocities, you integrate out the velocities, means that hydrodynamics should be irrelevant for the partition function that you calculate. But if hydrodynamics is then irrelevant, obviously this kind of hydrodynamic cosmic interaction should be zero. But the other people say, well, if we really calculate that, we see that we get a term that is not zero. But this is a very heavy calculation, and it's difficult to see where exactly the two approaches diverge. We're still working on that. Still papers coming out about this, let's call it Lipschitz conjecture on the hydrodynamic interaction, published in 1961. Still not clear that it's true or not. It will be, of course, it's very tempting to work on something where you can show that the great Lipschitz made a mistake. It's not so simple. It's not so simple. So we are approaching 11. I think I should just stop here and continue tomorrow, since I have enough time in these 3 days. Thank you.